Hey everyone! So we started looking into solving the challenges which are usually asked in the system design interviews. We already completed the challenge 1 about the 50 TB migration, and today we're looking at challenge 2. Again, just a quick disclaimer, this isn't exactly a getting started with Python type of video. We're going to be talking about spatial geometry, tree structures, and high concurrency architecture. If you're a beginner, you might find some of this a bit dense, but I'll try to build the intuition from the ground up, so stick with me. The setup for today is the Tinder problem. Basically, you're building a feature called Find Users Near Me. The requirement is simple. A user opens the app and you need to return a list of everyone within a 50-mile radius. Now, on the surface, this looks like a basic database query, right? You have a users table, you have a latitude column and a longitude column. You might think, okay, I'll just write a SQL query, something like select asterisk from users where distance of mylat, mylon, userlat, userlon, less than 50. This is what we call the naive approach, and in a small app with 1,000 users, it works perfectly. You don't even have to think about it. But if you're Tinder or Uber or any app at scale, this will absolutely melt your database. Why? Let's look at the physics. To calculate the distance between 2 points on a sphere, which is what Earth roughly is, you usually use the Haversine formula. It involves square roots, sines, and cosines. If you have 100 million users, every time one person opens the app, the database has to perform 100 million Haversine calculations. It's an O to N operation. If 10,000 people open the app at the same time, well, you're doing 1 trillion complex trigonometric calculations. Your CPU is just going to catch fire. You might say, well, I'll just put an index on the latitude and longitude columns. That helps a little, but not as much as you'd think. Standard B-tree indexes are one-dimensional. You can find everyone between latitude A and B very quickly, but then you still have to filter them by longitude, and then you still have to do the math to see if they are actually in the circle rather than just in a big box around you. So we have a fundamental indexing problem. How do we index two-dimensional space in a way that allows us to find nearby things without checking everything? Basically, we need a way to turn 2D coordinates into a 1D string or a hierarchy that a computer can actually search efficiently. This brings us to the core of the lecture, spatial indexing. So, the first real engineering solution most people look at is the grid. Imagine taking a map of the world and just drawing a giant grid over it. Every square in the grid has an ID. When a user is at lat long, you just map them to square number 502. When they want to find people nearby, you just look at square number 502 and maybe the 8 squares surrounding it. This is much better. It's O of 1, or O of constant, because you're only looking at a tiny subset of users. But it has a big flaw. How big should the squares be? If they're too big, you still have too much data in one square. If they're too small, like the size of a sidewalk, a 50-mile radius search would require checking thousands of squares. It's not flexible. This is where geohashing comes in. Geohashing is a really elegant hack. It takes your 2D coordinates and turns them into a single string of letters and numbers. It works by interleaving bits. You take the binary of the latitude and the binary of the longitude, and you just zip them together. The cool property of a geohash is that it's hierarchical. A short hash, like ABCD, represents a large area. A longer hash, like ABCD12, is a tiny area inside that large area. So if two hashes share the same prefix, let's say VZS8, it's a very high probability that they are physically close to each other. So in our Tinder app, we store every user's location as a geohash string in the database, and we put a standard string index on it. Now, when you want to find users near you, we just calculate your geohash and do a prefix search. But there's a gotcha here. It's called the edge problem. Imagine you are at the very, very edge of Geohash square A. Your neighbor is 5 feet away from you, but they are technically in Geohash square B. If you only search for people with your prefix, you'll never see your neighbor. To fix this, we don't just search your square, we calculate the geohash for your square plus the 8 surrounding neighbor squares. This is actually what a lot of production systems use. It's simple, it's fast, and it works with standard databases like Redis or Postgres. In fact, if you've ever used Redis GeoAdd and GeoRadius, that's exactly what it's doing under the hood. It's using a 52-bit integer geohash stored in a sorted set. But geohashing still has some weirdness near the poles, and the square nature of it doesn't always handle density well. Like, if you're in the middle of the Sahara Desert, one square might have 0 people. If you're in Times Square, NYC, that same size square might have 50,000 people. We need something that can zoom in where it's crowded and zoom out where it's empty. That brings us to the next level of the stack, Quadtrees. This is where it gets a bit more computer science-y, but it's actually very intuitive if you visualize it. Imagine a square representing the whole world. We check, are there more than 100 users in this square? If the answer is yes, we split that square into 4 smaller squares: northwest, northeast, southwest, southeast. Then we look at each of those 4 squares. If any of them have more than 100 users, we split them again. We keep doing this recursively until every leaf node in our tree has a manageable number of people. In NYC, the tree will be very deep. You might have squares that are only the size of a single building. In the ocean, you'll have one giant square that covers thousands of miles. This is great for performance because it balances the work the computer has to do. When you want to find users, you start at the top of the tree and you only follow the branches that intersect with your 50-mile circle. You can skip huge chunks of the world instantly. But there's a catch with Quadtrees, and this is a real-world catch: state. A quad tree is usually an in-memory data structure. If you have 100 million users and they are all moving, you have to constantly update the tree. If user A moves from NYC to New Jersey, they might move from one leaf node, which triggers a collapse of a branch, into another branch, which might trigger a split. Doing this in a thread-safe way at 100,000 writes per second, that is a nightmare. If you have one giant quad tree on one server, that server becomes a massive bottleneck. If you try to shard the quad tree, well, now you're doing cross-server tree traversals, and that's a whole different kind of pain. So how do the big players like Google or Uber do it? They usually move away from squares and look at something a bit more sophisticated: better hashing. Specifically, we should talk about Google's S2 library. So Google S2 is, honestly, it's kind of a work of art. It solves the problem of mapping a 2D sphere, the Earth, onto a 1D line. Wait, why a 1D line? Because computers are really good at searching lines. If you have a list of numbers in order, you can use binary search. It's incredibly fast. S2 uses what's called a space-filling curve, specifically a Hilbert curve. Imagine a piece of string that you wind through a grade in a very specific U-shaped pattern. You keep winding it until it touches every single square. The magic of the Hilbert curve is that it preserves locality. If 2 points are close to each other on the string, they are almost certainly close to each other in the 2D physical world. S2 takes this further. It projects the Earth onto the 6 faces of a cube, like a pair of dice, and then it covers each face with a Hilbert curve. It gives every single cell on Earth a 64-bit ID. The cool thing here is that you can represent a 50-mile circle not as a complex geometry, but as a collection of cell IDs. So when you search for users near me, the S2 library says, okay, your circle is covered by these 15 S2 cells.
Then you just go to your database, whether it's Cassandra, DynamoDB, or Bigtable, and you do a range scan for those 15 IDs. This is how you scale to billions of users. You've turned a 2D geometric search into a simple 1D range query on a key value store. It's stateless, it's sharding friendly, and it's mathematically robust. But we aren't done yet. This is system design, not just algorithm design. We need to talk about the actual architecture.
So, we've got S2 or geohashing for the math, but how do we handle the heat? Tinder has millions of active users, but it has even more inactive users. If you search for everyone within 50 miles and 90% of them haven't opened the app in a month, you're wasting a lot of energy. So, step 1 of the architecture, separate the heat and cold data. We only want to search the active users. We can keep a live location cache in Redis. When a user opens the app, we update their location in a Redis sorted set with an expiration time of, say, 30 minutes. Now, our search radius query only hits the active cache. It's 10x smaller and 100x faster. Next problem, hotspots. If you're in the middle of a music festival like Coachella or you're in Manhattan, you might have 100,000 users in a single square mile. Even with S2 cells, that's a lot of data to pull over the network and filter. This is where tiered querying comes in. You don't just ask for everyone in 50 miles, you ask for everyone in 2 miles. If that returns 500 people, you stop. You have enough for the UI. If it returns 0 people, you expand the search to 5 miles, then 10, then 50. And then there's the filter problem. Tinder isn't just about distance, it's about find people near me who are age 18 to 25 and who identify as X and who are active recently. If you do the spatial search first and get 5,000 people and then you filter them by age and gender in your app code, you're doing a lot of wasted work. But if you try to put age and gender into your spatial index, well, now your index is getting really complicated. The industry standard way to solve this is Elasticsearch, or a similar search engine. Elasticsearch has specialized geo-point fields. It actually uses a variation of the quadtree or geohash logic we talked about, but it combines it with an inverted index. So it can find people who are in cell number 502 and age equals 22 and gender equals female almost instantly. It's doing an intersection of 2 sets. But wait, Elasticsearch is slow for writes. If 100,000 people are moving every second, Elasticsearch will lag behind. So the final boss architecture looks like this. 1, you have a fast write store like Redis for the raw coordinates. This is the source of truth for where is this person right now. 2, you have a search index like Elasticsearch for the complex filtering. And 3, you have a stream processor like Flink or Kafka that takes the location updates from Redis and syncs them into the search index with a little bit of debouncing so you don't overwhelm the index. So let's wrap this up. We started with a simple SQL query, the naive approach, and saw that it fails because of the O of n physics of the Haversine formula. We looked at geohashing, which is the quick and dirty way to turn 2D into 1D using bit interleaving. We looked at Quadtrees, which are great for handling different densities of people, but are a pain to manage in memory at scale. And we looked at S2 cells, which use the Hilbert curve to give us a mathematically perfect way to map the sphere. The takeaway here isn't that you need to go implement a Hilbert curve today. Most of the time, you'll use a library like Google S2 or the built-in functions in PostGIS or Redis. The real system design takeaway is about reduction. How do you take a multi-dimensional, high-velocity problem and reduce it to something a standard database can handle? In Challenge 1, we reduced a migration to a log problem. In Challenge 2, we reduced a geometry problem to a string prefix or range scan problem.
This is the experienced senior engineer way of looking at systems. Don't look at the UI, look at the data, look at the bottlenecks, and look at the mathematical properties of the index. I'll put links to the S2 documentation and some great articles on the Hilbert curve in the description. If you're building something like this, I highly recommend reading the S2 white papers. They're pretty mind-blowing. Anyway, thanks for sticking through this. It was a long one, but spatial indexing is one of those foundational topics that every senior engineer should at least have the intuition for. As always, thanks for watching, and happy coding!